Hello, and welcome to this video about graphing velocity, position, and other data that will help us learn how to see changes in velocity. But first, you've probably heard of Bruno Mars, right? But have you heard of Bruno Jupiter? Yeah, that was awful. I apologize. That is terrible. Look, it's just like a bad Photoshop job. That's not even funny. Moving on. Alright. You may have seen, chances are, you've probably seen the movie The Martian. The Martian is a very cool movie, not only because it's fun, but also because certainly the author of the book, The Martian, went to great lengths to make sure that it was sort of scientifically logical, that the things in it were all totally plausible based on what we know about Mars and what we know about putting humans on another planet and stuff like that. So, if you don't know, the story is basically that Mark Watney, played by Matt Damon, is part of a crew on Mars, and while they are out exploring the surface, a storm comes in, forces the crew to suddenly leave the surface, and he gets left behind. They actually thought he was dead. He wasn't dead. He's just left behind with no way to say, hey, wait, I'm still down here. So, in the scene we're about to see, he finally does find a way to get off the surface of Mars and back to a craft waiting to pick him up. So let's just watch this, and then we'll look at it sort of data-wise afterwards. Craft is taking off from the surface of Mars. The Martian atmosphere is only 10% of the Earth's atmosphere, so it's much easier to get out of Mars' atmosphere. There were no windows left on this craft. Okay, so that was him taking off on the surface of Mars, and that is what we're going to explore in this video. So here's some data. Here's some data on his trip from the surface. So this is position time data. Position time data. Remember, not the same as distance time data. We're not necessarily interested in the distance that he covered so much as the position he is away from the start. So the start is at an altitude of 0, right? The surface of Mars. And as time goes on, right, this is in seconds, but it's basically like 1 minute, 2 minutes, 3 minutes, etc. You can see how the altitude has changed. So in this here, he's 600 meters above the surface, 1,500 meters above the surface, etc., etc. So those are sets of data that we can use as pairs to graph. And this is what it looks like when you turn it into a graph, right? So this is the altitude data, or essentially the position time graph for his flight from Mars. So you've got time on the x-axis, you've got altitude in meters on the y-axis, and this is basically tracing the change in position over time. So we can kind of look at this as two different parts of a graph, right? There's sort of two different things going on. One is that in the orange part here, in the first half or so, the slope of this line is actually changing. It's increasing, right? So it's steeper steeper up here, and it's not quite as steep here. When you get to the second half, the slope is constant, right? It's pretty much a straight line going in the same direction. Not completely straight, but pretty much straight. So that's what we want to focus on, is notice. And this would be, right, like as it's first trying to get off the ground, this is where it's moving the slowest. And then it starts to get a chance to pick up some speed. So we want to kind of compare these two areas and what they look like here. What we can also do at the same time is calculate the velocity for each interval. So you saw visually what the position data is going to look like. Now we can add in the velocity data. So how did I do this? I simply took the time interval, and the time interval is, or I'm sorry, the position interval. The position interval is each number subtracted by the one before it. So this is 600 minus 0. This is 1500 minus 600, which is 900, right? And then subtracting the previous times, right? 120 minus 60 is 60, right? And then divide to get the velocity numbers. And I did this in a spreadsheet, and it was very easy to do. So you can see here's the velocity data over time, and then I graphed it. So this is what it looks like if we graph velocity over each time interval. So at each time interval, you can see what the velocity was. And indeed, the velocity is going up and up. Not perfectly smoothly, but it's going up. And then finally, when you get to near the end of the trip, the velocity line becomes flat. It's totally horizontal. And hopefully you remember, a flat line has a slope of 0, right? It's not changing as a slope of 0. It's an important concept we want to emphasize. So let's see what it looks like when we connect these two graphs. So notice in this first part, when the slope is increasing in the position graph, slope is increasing in the position graph, the velocity is going up, right? It's not necessarily curving the same way. In fact, this is kind of roughly, with a few bumps in it, a linear increase in velocity for this nonlinear change in position. And then when you get to the constant slope from this part of the position graph, you see the flat slope here, the slope of 0. So this is still positive, but it's linear. So this turns into a flat slope here, right? So a constant change in altitude is a constant velocity. A nonlinear or non-constant change in slope is a linear change in velocity. So here are your takeaways for that we just saw. The slope of a position over time graph, just like we used with the altitude data, the slope of a position over time graph is velocity. So constant slope or linear indicates constant velocity, and constant velocity is shown as flat on a velocity graph. Changing slope, when it's nonlinear, indicates that the velocity is changing. We call this acceleration. And the slope of 0 on a position over time graph. The position graph has a slope of 0 or flat. It's just not moving, right? It's at a standstill. And then here is what you should take away about that's what's important. If you see a graph of velocity over time. So the slope of a velocity over time graph is acceleration. Acceleration, right? The positive slope of a velocity over time graph indicates it's accelerating in the positive direction. Generally speaking, we use right or east and up or north as our positives. So if it's accelerating positively, it's going in one of those directions. And the negative slope indicates that it's accelerating in the negative direction. Now, something that's moving in the positive direction but accelerating in the negative direction is slowing down and could actually still be moving in that positive direction. And then a slope of 0 on a velocity graph indicates that the velocity is constant. The object is still moving, but it's not accelerating. So that's something really to be careful about, is that slope means very different things on these different graphs. The slope of 0 on a position graph means not moving. The slope of 0 on a velocity graph means moving just at a constant velocity. All right? Hope that helped. Be sure you're taking notes on this. See you in the next one.